any linearly independent set of vectors can serve as a basis for the subspace. So we're going to be using the concepts that we've been going over the last 3 or 4 sections and apply that to a basis, to a coordinate system. And so if we have this subspace V, then and we have a set of vectors that are a basis. Remember the definition last time is we need a linearly independent set of vectors that span the subspace. So suppose that the span of the vectors is V and we have this basis. These vectors V sub 1, V sub 2 up through V sub n are linearly independent. Then any vector in the subspace can be written as a linear combination of the basis vectors. And that linear combination is unique. So the coordinates we can use this as a coordinate system, the new set of vectors, and we call them the B coordinates, right, because of this. And the B coordinates are just the coefficients in the linear combination that creates the vector. And so we'll check out an example in MATLAB. So we're going to ask ourselves, hey, what if we have a basis for R2? Right, these are two-dimensional vectors, and so how do we know that we have a basis? We'll have to check that these two vectors are linearly independent, but if they are, we'll have two linearly independent vectors, which means they can be a basis for R2, and then we can use those vectors to set up a coordinate system, which we're going to call the B coordinates. All right, and we've got two vectors. The first one is in standard coordinates, right? So just to remind you, the standard coordinates we would write as the vector E1, which is the 1, 0 vector, right? And the second vector, which we'll refer to as E2, is the vector 0, 1. So just remember that the columns of the identity matrix for that dimension are the standard basis vectors, 1, 0, 0, 1. In R3, it's 1, 0, 0, 0, 1, 0, and the third one is 0, 0, 1. All right, so if this vector is in standard coordinates, then we should be able to convert it to the B coordinates. And if we have a vector y that's already in the B coordinates, then we should be able to convert it to standard coordinates. So you'll notice that I have the matrix B, which is just the columns. Let me show this. It's just the columns of its columns are the basis vectors, right? And then to make everything work, I do have copies of the basis vectors. B1 is this B1 basis vector, and negative 5, 1 you see is the basis vector right here. So yes, these are my basis vectors, and let's just put the semicolons after them to keep them from displaying output. And so what do we want to do? Well, we want to convert this vector x into B coordinates. In our book, you can see what it means to find the B coordinates. The B coordinates of x means that we're solving this vector equation, right, for some x. Well, if x is in the subspace and we know that these vectors span it, then we know that there is some linear combination of the basis vectors that is equal to the vector x. But if we think of these vectors as columns, we actually just have an augmented matrix. This is our matrix. Call it matrix A if you'd like. And that's the columns. Its columns are the vectors of the basis. And then augmented on the other side, I have this vector x. So I'm just solving the same matrix equation that I've been solving forever. So let's go back to MATLAB. What we're trying to do, right, is we are looking at the augmented matrix Bx. right? So we're creating the matrix that looks like this. And when we row reduce and solve it, we'll get a linear dependence, right? We're saying that this set of vectors, if you think about three of them, is linearly dependent, right? The third one can be written as a linear combination of the first two because the first two serve as a basis for the entire space. So when we row reduce this, so I'm going to row reduce this augmented matrix with B and X. So then we find that the linear dependence relation is 1 minus 2. So I take 1 times the first vector minus 2 times the second vector. So if I write, if I want to write this vector x in b coordinates, right, it's the vector 1 minus 2. All right. And how do we verify that? Well, we're going to create this vector and just multiply it by the coordinate system and see if it works. So we can create, we'll call this xb, right? X capital B is this x with a subscript b, meaning that it's in the b coordinates. And we said that that should be 1 and negative 2. Those are its components, right? And if I take b times xb, right, then I get back to the vector that I had, right? This is my x vector here, right? 12, negative 4. And when I multiply the coordinate matrix times a vector that's in those coordinates, it converts it back to standard coordinates, which will give us a hint on how to solve the second piece, right? How am I going to solve to figure out what y is if y is presented in the b coordinates and I want to convert it to standard coordinates? All right, so now I have my y sub b vector here, right? You can see the 5 minus 4 is right here. And if I have a vector that's in the b coordinates, all I have to do is just multiply by the matrix. Now, with these matrix multiplications for linear transformations, which we're going to talk about, or which we've talked about, we're always talking about multiplying with the vector on the right and the matrix on the left. And the same thing is true here. So I take the b coordinate matrix, and I'm going to multiply by the vector y, which is in b coordinates, and then a straight multiplication will give me the solution of, and let me just put this in, right, because now this is the vector y, and I'm not going to put the subscript b with it. Why? Well, because it's in standard coordinates of 30 minus 14. Right? Why am I putting it in standard coordinates? Well, of course, I want to see if it works, right? So let me come down here and do the row reducing that we did before for x. So if I do the row reduced form of the augmented matrix b comma y, then I should get the original matrix back. And you see that the linear dependence relation that we come up with is 5 times the first vector minus 4 times the second. Well, you know what? Those are the b coordinates of y, right? So when we row reduce the augmented matrix, we're taking a vector that, okay, let me put it here, right? So if y is in standard coordinates, and then I row reduce, right? Put it with the coordinate matrix and row reduce, then I end up with the vector in beta coordinates. So this is if I row reduce. So I'll just put RREF here, right? So if I use RREF, then I go from the vector itself to the vector in b coordinates. And if I want to go back this way, right, I'll just put times, right? We're just multiplying. And so it's pretty straightforward. Let's look at an example from R3 next. Let's take a look at an example with 3 dimensions, right? So here, the 3 vectors m sub 1, n sub 2, and n sub 3 are a basis for R3. Oh, I said we should check. So let's actually do this and show, right? How do we verify that this is a basis for R3? Well, we do the row reduced form of M and make sure that it has 3 pivots, right? So as long as the row reduced form has 3 pivots, then we know that the 3 vectors are linearly independent, and anytime that we have 3 linearly independent vectors in R3, then we have a basis for all of R3. Okay, so now we're going to do the same thing. We are going to convert a vector that's in x coordinates, that is in standard coordinates, to the m coordinates. And how do we do that? Well, let's see. I have the x coordinate, the x vector here, right? Make sure that we have the right one. -9, 4, and -8 are its components. And what I need to do is row reduce the augmented matrix m comma x, and this will give me the linear dependence relation. So the vector x in the m coordinates is equal to the vector 3, -5, and 4. I'm sorry, this is this is poor. I'll apologize, but that's what we found. We found the vector x. We found the m coordinates for the vector x. And similarly, for the for a vector that's in m coordinates, what do? All I have to do is take the m matrix times the vector in m coordinates, and these are its standard coordinates. So this vector is equal to the vector y. Those are the standard coordinates of y. So that's how it goes. Changing coordinates is very easy, and we'll soon be talking about how to convert back and forth between, say, B coordinates and C coordinates. We can change between 2 different coordinate systems almost as easily as we can change in this way. So, and our last video is coming up. Will be very short, talking about the rank theorem, and that'll be posted soon.